When the James Webb Space Telescope began transmitting its first images back to Earth, astronomers knew they were about to witness something extraordinary. What they didn't anticipate was just how profoundly these observations would shake the foundations of our understanding of cosmic history. Within months of its deployment, Webb was revealing structures that shouldn't exist, galaxies that formed too quickly, and cosmic architecture that defied decades of carefully constructed theoretical models. The telescope wasn't just seeing further than we'd ever seen before. It was forcing us to reconsider everything we thought we knew about how the universe grew from its primordial state into the vast expanse we observe today. The story really begins with what scientists expected to find when they pointed Webb toward the earliest epochs of cosmic time. According to the standard cosmological model that had been refined over decades, the universe after the Big Bang went through a relatively predictable sequence of development. First came the initial expansion and cooling. Then, after about 380,000 years, the cosmos became transparent as electrons and protons combined to form neutral hydrogen atoms. This era, known as recombination, left behind the cosmic microwave background radiation that we can still detect today. Following this came what astronomers call the cosmic dark ages, a period lasting several hundred million years when the universe was filled with neutral gas, but no stars yet existed to light it up. Eventually, gravity began pulling matter together into increasingly dense clumps. The first stars were expected to form perhaps 100 to 200 million years after the Big Bang, and these early stellar objects would have been quite different from the stars we see today. They would have been massive, short-lived, and composed almost entirely of hydrogen and helium, since heavier elements didn't yet exist. These first-generation stars would then explode as supernovae, seeding the cosmos with heavier elements and triggering subsequent generations of star formation. Gradually, over hundreds of millions of years, these stars would collect into small proto-galaxies, which would then merge and grow into larger structures. The prevailing models suggested that massive, well-organized galaxies like our Milky Way took billions of years to assemble through this hierarchical process. When Webb turned its infrared gaze toward the deep universe, astronomers expected to see primitive, small, chaotic collections of stars. They anticipated finding the cosmic equivalent of construction sites, with raw materials still being assembled into something recognizable. Instead, what Webb revealed was astonishing. There, existing just a few 100 million years after the Big Bang, were massive galaxies that appeared remarkably mature. These weren't scattered groups of first-generation stars struggling to coalesce. They were substantial galactic structures containing billions of stars, showing signs of organized rotation, distinct morphological features, and levels of complexity that suggested a much more rapid formation process than anyone had predicted. One of the first bombshells came from observations of galaxies at redshifts beyond 6, 7, even reaching past 10. Redshift, for those less familiar with astronomical terminology, is a measure of how much the light from distant objects has been stretched by the expansion of the universe. The higher the redshift, the further away an object is, and the further back in time we're seeing it. Before Webb, galaxies at redshift 7 or 8 were considered extremely distant and rare. Webb started routinely identifying galaxies at these distances and beyond, pushing our observational window ever closer to the Big Bang itself. But the real surprise wasn't just how far Webb could see. It was what existed at those distances. Several galaxy candidates were identified that appeared to exist when the universe was only 300 to 400 million years old. To put this in perspective, if the current age of the universe were compressed into a single year, these galaxies would have formed in the first week of January. Yet they weren't cosmic newborns. Some displayed masses equivalent to billions of solar masses. They showed evidence of stellar populations that had already undergone considerable evolution. There were even hints of dust, which is created by dying stars and shouldn't exist in such quantities so early. The presence of dust was particularly puzzling because it takes time for stars to form, live out their lives, and die in explosions that scatter heavy elements and dust grains into space. Finding substantial dust in these early galaxies implied that multiple generations of stars had already come and gone. The initial reaction from the astronomical community was a mixture of excitement and healthy skepticism. Could these observations be correct? Were there systematic errors in how distances were being calculated? Determining the redshift of faint, distant galaxies is a complex process that relies on analyzing the spectrum of light they emit. With limited data, there's always room for misinterpretation. Some researchers suggested that what appeared to be extremely distant, ancient galaxies might actually be somewhat closer objects whose light was being affected by dust or unusual stellar populations that mimicked the signatures of high redshift. This kind of cautious approach is essential in science. Extraordinary claims require extraordinary evidence, and the astronomical community began the careful work of confirming or refuting these early findings. As more data accumulated and independent teams analyzed Webb's observations using different methods, the evidence became increasingly solid. Yes, some of the initial galaxy candidates turned out to be misidentified or at slightly lower redshifts than first thought, but many of the detections held up under scrutiny. Spectroscopic observations, which provide much more detailed information about an object's distance and properties than photometric estimates alone, confirmed that massive galaxies really did exist in the first few 100 million years after the Big Bang. The universe, it seemed, had gotten a much faster start than our models predicted. This discovery sent ripples through the field of cosmology. To understand why these findings were so disruptive, we need to appreciate what they mean for the standard model of galaxy formation. According to the lambda cold dark matter model, which has been the dominant framework for understanding cosmic structure formation, galaxies grow primarily through a bottom-up process. Dark matter, which makes up about 85% of the matter in the universe, forms an invisible scaffolding. This dark matter clumps together under gravity, creating potential wells into which ordinary matter falls. Small dark matter halos form first, and these gradually merge into larger halos over cosmic time. The ordinary matter within these halos cools, condenses, and forms stars, creating visible galaxies. This hierarchical assembly process is relatively slow, particularly in the early universe when matter was more diffuse and the expansion of space was working against gravitational collapse. Computer simulations based on this model had been remarkably successful at reproducing many features of the observed universe, from the large-scale structure of galaxy clusters and cosmic voids to the properties of individual galaxies we see today. But these same simulations consistently predicted that truly massive galaxies shouldn't exist at very high redshifts. There simply shouldn't have been enough time for dark matter halos to grow large enough and for sufficient gas to cool and form stars to create the behemoths that Webb was now detecting. The problem isn't just about time, it's about efficiency. Even if you imagine the most optimal conditions for star formation, there are physical limits to how quickly gas can collapse and turn into stars. Gas needs to cool down before it can fragment into star-forming clouds, and cooling takes time. As stars form, they inject energy back into their surroundings through stellar winds and supernova explosions, heating nearby gas and temporarily shutting down further star formation. This feedback process is crucial for preventing all the gas in a galaxy from turning into stars too quickly, which would create galaxies that look very different from what we observe in the nearby universe. Balancing star formation and feedback has been a major challenge in galaxy formation theory, and models had converged on scenarios that worked well for the relatively recent universe, but now seemed incompatible with these early, massive galaxies. Some researchers began calling these discoveries impossible galaxies, a term that captured the sense of bewilderment they provoked. Of course, they weren't truly impossible since they clearly existed. The term really meant impossible according to our current understanding. And that's where things get really interesting for science. When observations clash with theory, something has to give. Either the observations are wrong, which becomes less likely as confirming evidence accumulates, or the theory needs to be revised, sometimes dramatically. Several possibilities emerged as astronomers grappled with Webb's revelations. One hypothesis focused on the initial conditions of the universe. Perhaps the density fluctuations in the early cosmos were larger in amplitude than we thought, creating deeper potential wells that could attract matter more efficiently. These enhanced density fluctuations would need to be consistent with observations of the cosmic microwave background, which provides a snapshot of the universe when it was only 380,000 years old. The microwave background appears remarkably smooth, with only tiny variations in temperature and density from place to place. These variations are the seeds from which all cosmic structure grew. If structure formation happened faster than expected, maybe those seeds were somehow more potent than we realized, or perhaps they translated into galaxy formation more efficiently through mechanisms we hadn't fully understood. Another line of thinking questioned our assumptions about star formation itself. What if stars in the early universe form much more rapidly and efficiently than in the present-day cosmos? The first stars were born in an environment completely devoid of heavy elements, since these elements are forged inside stars and scattered by stellar explosions. This pristine chemical composition might have allowed gas clouds to fragment differently, potentially creating conditions for extremely rapid star formation. Some models suggested that early star formation might have proceeded in intense bursts, converting gas into stars at rates far exceeding what we see in nearby galaxies. If this were true, a galaxy could assemble its stellar mass much faster than gradual, steady star formation would allow. There's also the question of dark matter itself. Dark matter remains one of the great mysteries of modern physics. We know it exists because we can see its gravitational effects on visible matter, on the rotation of galaxies, on the motion of galaxy clusters, and on the path light takes as it travels through the universe. But we still don't know what dark matter actually is. The leading candidate has been cold, dark matter, consisting of particles that move slowly compared to the speed of light and that interact only through gravity. This type of dark matter produces the hierarchical structure formation we mentioned earlier. But what if dark matter has properties we haven't accounted for? What if it interacts with itself in subtle ways? Or if it experienced a phase transition in the early universe that altered how it clumped together? Such modifications could potentially allow dark matter halos to assemble faster than standard cold dark matter predicts, enabling earlier and more rapid galaxy formation. Some researchers have even begun reconsidering more exotic alternatives, including modifications to our understanding of gravity itself. Modified gravity theories like MOAND, which stands for Modified Newtonian Dynamics, have been proposed over the years as alternatives to dark matter. While these theories have struggled to match the full range of cosmological observations, the surprising findings from Webb have prompted some scientists to give them a fresh look. Could there be something about gravitational physics on cosmic scales that we're missing? It's a radical suggestion, and most astronomers remain skeptical. But the unexpected nature of Webb's discoveries has opened doors to conversations that might have been dismissed out of hand just a few years ago. Beyond the sheer existence of these early massive galaxies, Webb has revealed other perplexing features that compound the puzzle. Some of these ancient galaxies appear to have remarkably ordered structures. Astronomers have detected disk-like shapes and even hints of spiral arms in galaxies that formed less than 1 billion years after the Big Bang. This is surprising because galaxy disks are thought to form gradually as gas settles into rotational equilibrium within a dark matter halo, and spiral arms typically arise from density waves in mature disk galaxies. Finding such features so early suggests that galaxies achieved stability and organization much faster than anticipated. It's like discovering that ancient human civilizations had developed sophisticated architecture and urban planning just a few generations after first learning to build shelters. The colors and spectra of these early galaxies have also yielded surprises. By analyzing the light they emit at different wavelengths, astronomers can infer the ages and types of stars present. Some of these galaxies show evidence of stellar populations that appear quite old relative to the age of the universe at that time. If you observe a galaxy when the universe is 500 million years old and the stars in that galaxy appear to be 300 million years old, that means star formation began extraordinarily early and proceeded rapidly. There are also spectral features indicating the presence of heavier elements like oxygen and carbon, which again points to multiple generations of stars having already lived and died. Each generation of stars enriches the interstellar medium with heavier elements. So detecting these elements early means the cosmic chemical evolution happened faster than expected. Webb's infrared capabilities have been crucial for these discoveries. The telescope was specifically designed to observe in infrared wavelengths, which is essential for studying the distant universe. As light travels across billions of light years, the expansion of the universe stretches its wavelength, shifting it toward the red end of the spectrum and beyond into the infrared. The further away an object is, the more its light is redshifted. For the most distant galaxies, even ultraviolet light emitted by hot young stars gets shifted all the way into the infrared by the time it reaches us. Previous space telescopes like Hubble operated primarily in visible and ultraviolet wavelengths with some infrared capability. Webb, by contrast, is optimized for infrared observation, allowing it to detect these highly redshifted galaxies that would be invisible or barely perceptible to other instruments. The engineering behind Webb's infrared capabilities represents decades of innovation. Its primary mirror stretches 6.5 meters across, composed of 18 hexagonal segments made from beryllium and coated with a microscopically thin layer of gold. This configuration gives Webb roughly 6 times the light-collecting area of Hubble, allowing it to detect extremely faint objects. But size alone isn't enough. Infrared light also means heat, and any thermal emission from the telescope itself would overwhelm the faint signals from distant galaxies. To solve this problem, Webb operates at incredibly cold temperatures, kept below 50 Kelvin by a massive sun shield the size of a tennis court. This 5-layer shield blocks radiation from the sun, Earth, and Moon, creating a permanently shadowed environment where the telescope's instruments can function with minimal interference. Positioned at the second Lagrange point, roughly 1.5 million kilometers from Earth, Webb occupies a gravitationally stable location that allows it to maintain its orbit with minimal fuel expenditure while keeping its sun shield between its instruments and the bright inner solar system. From this vantage point, it has an unobstructed view of deep space, free from the thermal glow and reflected light that would compromise its observations closer to Earth. When Webb turned its gaze toward regions of sky previously observed by Hubble and other telescopes, astronomers expected to find some early galaxies. They knew from theoretical models and previous deep field observations that galaxy formation should have begun several 100 million years after the Big Bang. What they didn't anticipate was how many galaxies they would find, or how developed these galaxies would appear. The first images released to the public in July 2022 already hinted at surprises. Webb's deep field image revealed thousands of galaxies in a tiny patch of sky, many of them appearing as faint red smudges indicating extreme distances. As astronomers began analyzing the data in detail, measuring redshifts and estimating distances, a pattern emerged that contradicted expectations. Galaxies were appearing at redshifts corresponding to times when the universe was only a few 100 million years old, during what's known as the cosmic dawn. But these weren't the small, primitive proto-galaxies that models predicted. Many showed signs of being massive systems containing billions of stars, with structures suggesting they had already undergone significant evolution. One particularly striking example emerged from observations of a galaxy designated Glass Z13, which appeared to exist when the universe was approximately 300 million years old. Based on its brightness and spectral properties, astronomers estimated it contained a stellar mass equivalent to 1 billion suns. Finding such a massive galaxy at this early epoch was like discovering a fully grown tree in what should have been freshly planted soil. According to standard models of hierarchical structure formation, galaxies should grow gradually through mergers and accretion, starting small and building up over time. Yet here was evidence of a massive, seemingly mature galaxy existing when the universe itself was still in its infancy. As more data accumulated, the picture became increasingly puzzling. Multiple surveys using Webb detected numerous massive galaxy candidates at similar early epochs. Some showed evidence of complex morphologies with disc-like structures or even spiral arm features. Others displayed spectral signatures indicating active star formation or the presence of older stellar populations. Each new discovery added to a growing body of evidence suggesting that galaxy formation in the early universe proceeded much more rapidly and efficiently than previously thought possible. The implications of these discoveries ripple through multiple areas of cosmology and astrophysics. The standard model of structure formation, known as lambda CDM, describes how tiny quantum fluctuations in the early universe grew under gravity into the cosmic web of galaxies we see today. This model has been remarkably successful in explaining many observations, from the cosmic microwave background to the large-scale distribution of galaxies. It predicts that structure formation should proceed hierarchically, with small dark matter halos forming first, and gradually merging to create larger structures. Gas falling into these halos would cool and condense to form stars, building up galaxies over hundreds of millions of years. Under this framework, there should be strict limits on how massive a galaxy can become by any given cosmic epoch. The available time for gas to cool, collapse, and form stars imposes constraints on how quickly galaxies can grow. The presence of massive galaxies just a few 100 million years after the Big Bang pushes against these limits in uncomfortable ways. Either something about our understanding of early star formation is incomplete, or the conditions in the early universe were dramatically different from what models assume, or the lambda CDM framework itself requires modification. One possibility is that star formation in the early universe was far more efficient than in nearby galaxies. In the present-day universe, only a small fraction of available gas in galaxies actually forms stars. Various feedback processes, such as stellar winds, supernova explosions, and radiation from massive stars, heat and disperse gas, regulating star formation and preventing it from converting all available material into stars. Perhaps in the early universe, before heavy elements had been widely distributed, and before the intergalactic medium had been enriched with metals, these feedback processes operated differently. Maybe the first generations of stars formed more efficiently from the pristine hydrogen and helium left over from the Big Bang, allowing galaxies to build up stellar mass more quickly than current models suggest. Another consideration involves the nature of the first stars themselves. The very first generation of stars, known as population 3 stars, formed from gas containing only hydrogen and helium with trace amounts of lithium. Without heavier elements to facilitate cooling, this primordial gas could only collapse into very massive stars, potentially hundreds of times the mass of the Sun. These behemoths would have burned brilliantly but briefly, ending their lives in spectacular supernovae that enriched their surroundings with the first heavy elements. If these first stars were indeed much more massive than typical stars forming today, they might have contributed differently to the buildup of stellar mass and light in early galaxies. However, population 3 stars remain largely theoretical, since none have been directly observed, and their exact properties remain uncertain. The role of dark matter in early structure formation also comes under scrutiny. Dark matter, which makes up roughly 85% of all matter in the universe, doesn't interact with light, but exerts gravitational influence. Its presence is inferred from galaxy rotation curves, gravitational lensing, and large-scale structure formation. In the Standard Model, dark matter provides the gravitational scaffolding upon which galaxies form. Small dark matter halos collapse first, creating gravitational wells into which normal matter falls and eventually forms stars. The properties of dark matter, particularly how it clumps on small scales, directly affect how quickly and efficiently galaxies can form. Most cosmological models assume dark matter is cold, meaning its particles move slowly compared to the speed of light. Cold dark matter clumps readily on all scales, allowing structure to form efficiently at both large and small sizes. But if dark matter has different properties than assumed, perhaps being slightly warm with particles moving faster, or if it interacts weakly with itself or other particles in ways not yet discovered, the rate of structure formation could differ from predictions. The rapid assembly of massive galaxies suggested by Webb's observations might indicate that dark matter clumps more efficiently than models predict, or that it interacts with normal matter in unexpected ways during the early universe. Some researchers have proposed more exotic explanations. A few suggest that the early universe might have contained primordial black holes formed directly from density fluctuations shortly after the Big Bang rather than as remnants of dying stars. These black holes could have served as seeds around which gas accumulated and formed stars more rapidly than in the standard bottom-up scenario. While speculative, this idea illustrates how Webb's discoveries are prompting astronomers to reconsider fundamental assumptions about the early universe. The observations also raise questions about the role of supermassive black holes in early galaxy evolution. Most large galaxies today host supermassive black holes at their centers, with masses ranging from millions to billions of times the Sun's mass. These black holes can dramatically influence their host galaxies through powerful jets and radiation that heat surrounding gas and regulate star formation. Some of the early galaxies observed by Webb show signs of active galactic nuclei, indicating the presence of growing supermassive black holes. The existence of such massive black holes so early in cosmic history presents its own puzzle, since there hasn't been much time for them to grow through accretion. Understanding how both galaxies and their central black holes grew so rapidly in the early universe represents a major challenge for theoretical models. It's worth noting that not all astronomers agree on the interpretation of Webb's observations. Science proceeds through careful analysis, debate, and verification, and the discoveries remain subject to ongoing scrutiny. Some of the initial mass estimates for early galaxies relied on photometric redshifts, which are derived from measuring brightness in multiple filters, but can be less precise than spectroscopic redshifts obtained from detailed spectral analysis. As more spectroscopic follow-up observations are completed, some of the most extreme early galaxy candidates may turn out to be at somewhat less dramatic distances, or their masses may be revised downward. Dust within galaxies can also affect brightness measurements, potentially leading to overestimates of stellar mass if not properly accounted for. Additionally, some researchers argue that the observations might be explained within existing frameworks if certain parameters are adjusted. Perhaps star formation efficiency in the early universe was at the high end of what current models allow, or perhaps the initial conditions following the Big Bang included slightly larger density fluctuations than typically assumed. These adjustments would push the limits of existing theories, but wouldn't require abandoning the fundamental structure of the lambda CDM model. Nevertheless, even accounting for uncertainties and potential revisions, the overall pattern emerging from Webb's observations suggests that something interesting is happening in the early universe. Multiple independent teams have reported similar findings, and the sheer number of massive galaxy candidates at high redshifts exceeds what most models predicted. This consistency across different surveys and analysis methods strengthens the case that the observations reflect genuine features of the early universe rather than systematic errors or misinterpretations. The scientific community has responded with characteristic energy, producing numerous papers exploring possible explanations and conducting follow-up observations to better constrain the properties of these early galaxies. Conferences and workshops have focused specifically on the implications of Webb's discoveries, bringing together observers and theorists to compare results and refine models. This burst of activity exemplifies how unexpected observations drive scientific progress, challenging researchers to think creatively and test the boundaries of established theories. Beyond the specific question of massive early galaxies, Webb has revealed other surprising aspects of the early universe that complicate the picture of cosmic evolution. Observations have detected surprisingly large amounts of dust in some early galaxies, for instance. Dust consists of tiny solid particles formed from heavy elements produced by stars and dispersed through supernova explosions. The presence of substantial dust in galaxies existing just a few 100 million years after the Big Bang suggests that multiple generations of stars had already lived and died, further evidence that evolution proceeded rapidly in the early universe. Webb has also observed early galaxies with unexpectedly strong emission lines from ionized oxygen, carbon, and other elements. These emission lines indicate active star formation and the presence of hot gas heated by ultraviolet radiation from young, massive stars. The strength of these lines, combined with the galaxy's brightness, suggests vigorous star-forming activity occurring at cosmic epochs previously thought to represent the earliest phases of galaxy assembly. Instead of catching galaxies in the act of forming their first stars, Webb often seems to be observing systems already in full swing, churning out stars at prodigious rates. The morphology of early galaxies presents another intriguing aspect. While many appear as small, compact blobs, some show elongated or irregular structures suggesting ongoing mergers or chaotic assembly processes. A few even display hints of organized structures like disks or bar features, which in nearby galaxies take time to develop through gravitational interactions and angular momentum redistribution. Finding such structures in the early universe implies that galaxies could develop ordered morphologies more quickly than expected, perhaps because gas was denser and interactions were more frequent in the compact early universe. These observations connect to broader questions about when and how galaxies acquired their present-day diversity. Today's universe contains spiral galaxies with organized disks and spiral arms, elliptical galaxies with smooth, featureless appearances, and irregular galaxies lacking clear structure. Understanding how these different types emerged and evolved over cosmic time remains an active area of research. Webb's ability to observe galaxies in the early universe provides snapshots of this evolutionary process, revealing the ancestral populations from which modern galaxies descended. The telescope has also contributed to understanding the epoch of reionization, a crucial transition in cosmic history when the universe changed from being mostly neutral to mostly ionized. After the Big Bang, the universe initially consisted of hot, ionized plasma. As it expanded and cooled, protons and electrons combined to form neutral hydrogen atoms, about 380,000 years after the Big Bang. This neutral phase persisted for hundreds of millions of years, until the first stars and galaxies formed. Ultraviolet radiation from these early sources gradually reionized the hydrogen throughout space, creating bubbles of ionized gas that grew and merged until the entire universe became ionized again. This process, the epoch of reionization, fundamentally altered the properties of intergalactic space and affected subsequent galaxy formation. Previous observations had constrained when reionization occurred, suggesting it was largely complete by about 600 million years after the Big Bang, though the exact timing and progression remained uncertain. Webb's observations of early galaxies help refine this picture by identifying the sources responsible for reionization and tracking how ionized regions grew over time. Some studies have detected galaxies at the edge of ionized bubbles, their light partially absorbed by intervening neutral hydrogen, providing direct evidence of the reionization process in action. Interestingly, tallying up the ultraviolet light from all known galaxies in the relevant epoch initially suggested there might not be enough radiation to complete reionization. This finding led to speculation about additional sources, perhaps very faint dwarf galaxies below Webb's detection limit, or more exotic possibilities like decaying dark matter particles or primordial black holes. However, more recent analyses suggest that early galaxies might produce more ionizing photons than initially estimated, perhaps because their stellar populations differ from those in nearby galaxies, or because dust absorption is less significant than assumed. The question remains an area of active investigation. Webb's discoveries also intersect with the ongoing debate about the Hubble tension, a puzzling discrepancy between different measurements of the universe's expansion rate. The Hubble constant describes how fast the universe is expanding, and its value affects calculations of cosmic age, distances, and the history of structure formation. Measurements based on observations of the nearby universe, using methods like supernovae and Cepheid variable stars, yield a Hubble constant of about 73 kilometers per second per megaparsec. But measurements derived from the cosmic microwave background, combined with the lambda CDM model, give a value closer to 67. This difference, though seemingly small, persists across many independent measurements and exceeds the estimated uncertainties, suggesting it might reflect real physics rather than measurement errors. If the higher value is correct, the universe is expanding faster than the standard model predicts, which would mean it's younger than calculated. A younger universe would allow even less time for massive galaxies to form, making Webb's observations of early massive galaxies even more difficult to explain within the standard framework. Conversely, if something about the lambda CDM model needs revision to explain the Hubble tension, those same revisions might also affect predictions for early galaxy formation. The two puzzles might be related, both pointing toward gaps in our understanding of cosmic expansion and structure formation. Addressing these mysteries will require both additional observations and theoretical advances. Webb will continue observing the early universe, building larger samples of high redshift galaxies and obtaining detailed spectroscopic data to better constrain their properties. Complementary observations from other telescopes, including ground-based facilities and eventually future space missions, will provide additional perspectives. Meanwhile, theorists will refine simulations of galaxy formation, exploring different scenarios for star formation efficiency, dark matter properties, and feedback processes. One promising avenue involves improving simulations of the first billion years of cosmic history. Modern cosmological simulations can model the formation of structure across vast volumes of space, but capturing all the relevant physics remains computationally challenging. Simulations must account for gravity, gas dynamics, star formation, chemical enrichment, black hole growth, magnetic fields, cosmic rays, and numerous feedback processes, all operating across scales ranging from individual stars to galaxy clusters. Increasing computing power and better algorithms allow progressively more detailed simulations, but there's always a tension between the volume simulated and the resolution achieved. Understanding early galaxy formation might require new approaches that balance these competing demands differently. Observations from Webb are already informing these efforts by revealing which aspects of early galaxies are most surprising and require explanation. For instance, if most early massive galaxies turn out to have formed through unusually efficient star formation rather than through early dark matter halo assembly, simulations can focus on understanding what physical conditions would enhance star formation efficiency. If instead the galaxies formed in unusually massive dark matter halos that assembled earlier than expected, attention would shift to understanding the growth of structure in the first few 100 million years after the Big Bang. Another important direction involves better understanding the stellar populations in early galaxies. Stars of different masses and ages contribute differently to a galaxy's total light and mass. Massive hot stars are very bright in ultraviolet light but short-lived, while lower mass, cooler stars are dimmer but can shine for billions or even trillions of years. The mix of stellar types in a galaxy, called its stellar population, affects how we interpret its observed light. Distinguishing between a young galaxy forming its first massive stars and an older galaxy containing a mix of stellar ages requires detailed analysis of spectral features, something Webb is uniquely capable of providing. Webb's near-infrared spectrograph can split light from distant galaxies into its component wavelengths, revealing absorption and emission lines from various elements. These spectral features act like fingerprints, indicating which elements are present, their temperatures, and their motions. By analyzing these lines, astronomers can determine not just a galaxy's distance but also its chemical composition, star formation rate, and the ages of its stellar populations. Such information is crucial for understanding whether seemingly massive early galaxies are truly as evolved as they appear, or whether their properties can be explained by specific stellar populations that are luminous, but not necessarily long-lived. Chemical abundances provide particularly valuable clues. The first stars formed from primordial gas containing only hydrogen and helium, with trace lithium. These stars produced heavier elements like carbon, nitrogen, oxygen, and iron through nuclear fusion, then dispersed these elements into space when they died. Subsequent generations of stars formed from gas, enriched with these heavy elements, gradually increasing the metallicity of galaxies over time. Measuring the abundance of heavy elements in early galaxies reveals how many stellar generations have already occurred, constraining how rapidly stars formed and died in the first few 100 million years after the Big Bang. Some Webb observations have detected surprisingly high metallicities in certain early galaxies, suggesting rapid chemical enrichment. This finding implies vigorous star formation and multiple supernova explosions in quick succession, further evidence that evolution proceeded rapidly. However, other early galaxies show lower metallicities closer to predictions, indicating diversity in enrichment histories. Understanding this diversity and what drives different evolutionary paths represents another frontier in the study of early galaxies. The relationship between galaxies and their surrounding intergalactic medium also matters for understanding early evolution. Galaxies don't exist in isolation, but are embedded in a cosmic web of dark matter and gas. Gas falling into galaxies from the intergalactic medium provides fuel for star formation, while feedback from stars and black holes ejects gas back into intergalactic space. This continuous exchange regulates galaxy growth and affects the properties of both galaxies and the intergalactic medium. In the early universe, when galaxies were closer together and the intergalactic medium was denser, and these interactions might have been more intense and influential than in the modern universe, the James Webb Space Telescope has given astronomers an unprecedented view of this critical period of cosmic exchange and galaxy building. By observing galaxies in unprecedented detail during epochs when the universe was only a few 100 million years old, Webb has revealed that these early galaxies weren't just glowing collections of stars, but dynamic systems already engaged in complex physical processes. The telescope has detected evidence of powerful stellar winds, supernova explosions, and even active supermassive black holes in galaxies that existed when the universe was supposedly still in its infancy. This discovery has profound implications for our understanding of how quickly galaxies can develop the sophisticated machinery needed to regulate their own growth. One particularly striking finding involves the detection of what appears to be mature stellar populations in some of these early galaxies. When astronomers analyze the light from distant galaxies, they can determine not just how many stars are present, but also their ages and chemical compositions. The spectrum of light from a galaxy acts like a fingerprint, revealing whether the stars are young and hot or older and cooler. Webb's observations have identified galaxies that contain what seem to be relatively old stars, meaning stars that had already been burning for hundreds of millions of years by the time we observe them. This presents a mathematical puzzle, because if stars are already hundreds of millions of years old when the universe itself is only 500 or 600 million years old, then star formation must have begun extremely early in cosmic history, perhaps within the first 100 million years after the Big Bang. This timeline compression challenges astronomers to reconsider the sequence of events that led to the first stars and galaxies. The traditional picture held that the first stars, known as population 3 stars, were massive objects composed almost entirely of hydrogen and helium, because heavier elements hadn't yet been manufactured. These primordial stars would have lived fast and died young, exploding as supernovae and seeding the cosmos with the first heavy elements. Only after this initial generation would subsequent generations of stars and eventually galaxies begin to form. Webb's data suggests this process might have unfolded much more rapidly than previously thought, with galaxies assembling and developing complex stellar populations on timescales that seem almost impossibly short. The presence of heavy elements in early galaxies presents another piece of the puzzle. Heavy elements are created inside stars through nuclear fusion and distributed into space when stars explode as supernovae or shed their outer layers. The more generations of stars that have lived and died, the more heavy elements accumulate in the gas from which new stars form. Astronomers use the abundance of heavy elements as a kind of cosmic clock, estimating how much stellar processing has occurred. Webb has detected surprisingly high levels of heavy elements in some very early galaxies, suggesting that multiple generations of stars had already cycled through their lifetimes by the time these galaxies were only a few 100 million years old. This rapid chemical enrichment implies that star formation and stellar death were proceeding at an extraordinary pace in the early universe. The discovery of supermassive black holes in the early universe has added another layer of complexity to our understanding of cosmic evolution. Supermassive black holes, which can contain millions or even billions of times the mass of our Sun, reside at the centers of most large galaxies today, including our own Milky Way. The relationship between these black holes and their host galaxies appears to be intimate and important, with the mass of the central black hole correlating with properties of the surrounding galaxy, such as the mass of its central bulge of stars. This relationship suggests that galaxies and their central black holes grow together in some coordinated fashion, influencing each other's development through feedback processes. Webb has identified what appear to be active, supermassive black holes in galaxies that existed when the universe was less than 1 billion years old. These black holes are revealed by the intense radiation they emit as they consume surrounding gas and dust, creating brilliant beacons called quasars, or active galactic nuclei. The problem is that black holes grow by accumulating matter, and there are theoretical limits to how quickly this process can occur. The most efficient growth mechanism involves gas spiraling into the black hole through an accretion disk, heating up and emitting radiation as it falls inward. However, this radiation creates outward pressure that pushes against the infalling gas, limiting how fast the black hole can grow. This limit is known as the Eddington limit, and it sets a maximum rate at which a black hole can accumulate mass. Given these growth rate constraints, astronomers can calculate how long it would take a black hole to reach a certain mass starting from some initial seed. The supermassive black holes that Webb has detected in the early universe are so massive that even if they started growing at the maximum possible rate from the moment the first stars formed, it's challenging to explain how they could have reached their observed masses so quickly. This suggests either that black hole seeds in the early universe were somehow much more massive than expected, or that black holes found ways to grow faster than the theoretical limits would suggest, or that our understanding of black hole formation and growth needs revision. Several theoretical models have been proposed to address this black hole growth problem. One possibility is that the first black holes formed not from the deaths of individual stars, but through the direct collapse of massive gas clouds. Normally, Gas clouds fragment as they collapse, forming many smaller stars rather than a single massive object. But under certain conditions, a gas cloud might collapse directly into a massive black hole without ever forming stars. These direct collapse black holes could have initial masses thousands or even tens of thousands of times that of the Sun, giving them a significant head start on the growth process. Another possibility is that black holes in the early universe grew through rapid mergers, with many smaller black holes combining to create larger ones. In the denser environment of the early universe, such mergers might have occurred frequently enough to build up supermassive black holes on short timescales. Webb's observations have also raised questions about the role of dark matter in galaxy formation. Dark matter doesn't interact with light and can only be detected through its gravitational effects on ordinary matter and light. Most of the matter in the universe is thought to be dark matter, and galaxies are believed to form within vast halos of this mysterious substance. The gravitational pull of dark matter halos provides the scaffolding around which ordinary matter can accumulate and form stars. Computer simulations of galaxy formation incorporate dark matter and show how galaxies should build up over time within these dark matter frameworks. The standard model of cosmology, known as lambda cold dark matter or LCDM, makes specific predictions about how structure should form in the universe. In this model, dark matter is cold, meaning it moves slowly compared to the speed of light, and it clumps together under gravity in a bottom-up fashion, with small structures forming first and then merging to create larger structures over time. This hierarchical assembly process should mean that the largest, most massive galaxies form relatively late in cosmic history, after many smaller galaxies have merged together. Yet Webb has found what appear to be quite massive galaxies very early on, seemingly inconsistent with this bottom-up growth pattern. This apparent discrepancy has led some researchers to wonder whether the properties of dark matter might be different from what LCDM assumes. Perhaps dark matter is warmer than thought, moving faster and thus smoothing out structure on small scales while allowing large structures to form more quickly. Or perhaps dark matter interacts with itself in ways that standard models don't account for, affecting how rapidly structures can collapse and grow. These are speculative ideas and would require significant revisions to our understanding of fundamental physics, but the unexpected findings from Webb have made such possibilities worth considering and investigating. Of course, it's important to remember that initial interpretations of new observations can be revised as more data accumulates and as analysis techniques improve. The earliest Webb results that suggested impossibly large galaxies in the very early universe have been subject to ongoing scrutiny. Some of those initial distance estimates have been refined with more detailed spectroscopic observations, in some cases moving galaxies to slightly later epochs where their properties are less problematic for theoretical models. Additionally, astronomers have recognized that inferring galaxy properties from limited data involves assumptions that might not always hold, especially for galaxies that might differ significantly from those in the nearby universe that we know better. For instance, estimating stellar mass from observations requires assumptions about the initial mass function, which describes the distribution of masses among newly formed stars. If the early universe produced a different mix of stellar masses than we see in nearby galaxies today, then mass estimates based on modern templates could be significantly off. Similarly, the presence of active galactic nuclei, where supermassive black holes are actively feeding, can add light that might be mistaken for starlight, potentially leading to overestimates of stellar mass. As astronomers have worked to account for these complications, some of the most extreme early mass estimates have been revised downward, easing the tension with theoretical models somewhat. Nevertheless, even with these refinements, Webb has unquestionably shown that galaxies in the early universe were more abundant, more massive, and more structurally developed than standard models predicted. This isn't necessarily a crisis for cosmology, but it does indicate that our models need adjustment. The universe clearly found ways to build galaxies more efficiently in its early epochs than our simulation suggested, and understanding exactly how this happened is one of the great challenges now facing astronomers. One area of particular interest is understanding the efficiency of star formation in the early universe. Star formation efficiency refers to what fraction of available gas actually gets converted into stars, as opposed to being blown away by stellar winds or failing to collapse due to turbulence in magnetic fields. In the local universe, star formation is actually a rather inefficient process. Most of the gas in a galaxy doesn't immediately form stars. and various feedback processes regulate the rate at which star formation proceeds. But in the early universe, conditions might have been different in ways that allowed stars to form more readily from available gas. The gas in early galaxies might have been able to cool more efficiently, allowing it to collapse into dense clouds where stars could form. Or perhaps the intense ultraviolet radiation from massive young stars in early galaxies had a different effect than it does in modern galaxies, either triggering additional star formation by compressing gas clouds or suppressing it by heating and dispersing gas. The interplay between star formation and feedback processes is complex, and might have operated differently when galaxies were younger, more compact, and more gas-rich than they are today. Webb's ability to analyze the chemical composition of early galaxies provides important clues about these processes. By measuring the abundances of different elements in the gas and stars of early galaxies, astronomers can trace how efficiently stars formed and how effectively supernovae and stellar winds distributed heavy elements back into the interstellar medium. Some early galaxies show surprisingly uniform chemical compositions, suggesting that gas was well mixed through vigorous stellar feedback. Others show chemical variations that might indicate different star formation histories in different parts of the galaxy. The structure and morphology of early galaxies has also been a source of surprises. When astronomers first began observing distant galaxies with the Hubble Space Telescope, they noticed that high redshift galaxies often appeared irregular and clumpy, quite different from the elegant spiral and elliptical galaxies common in the nearby universe. This made sense in the context of hierarchical galaxy formation, where early galaxies would be undergoing frequent mergers and would not yet have settled into stable, organized structures. Webb has revealed even more detail in the structures of early galaxies, showing that some already display features like disks, bars, and spiral arms that were thought to develop only later in cosmic history. The presence of these organized structures raises questions about how quickly galaxies can settle into stable configurations after forming. A rotating disk of stars is a structure in equilibrium, where the inward pull of gravity is balanced by the outward centrifugal force from rotation. For a galaxy to develop and maintain such a disk, it needs time to settle down after violent formation events like mergers. The fact that some galaxies only a few 100 million years after the Big Bang already show disk-like structures suggests either that they formed more smoothly than expected, without the disruptive mergers that would destroy a disk, or that disks can form and stabilize more quickly than theoretical models predict. Spiral arms and bars, which are common features of disk galaxies in the local universe, are thought to arise from gravitational instabilities in rotating disks. The fact that Webb has detected what appear to be these features in some early galaxies indicates that the physical processes governing disk dynamics were already operating in the young universe. This is exciting because it suggests that some of the basic mechanisms that shape galaxies have been in place throughout most of cosmic history, even if the overall environment and conditions have changed dramatically. Webb has also provided insights into how galaxies interact with their surroundings. Galaxies don't exist in isolation, but are embedded in a cosmic web of dark matter and gas filaments. Gas flowing along these filaments and into galaxy halos provides the fuel for ongoing star formation. Webb has detected evidence of this cosmic web structure even at high redshifts, observing the patterns of galaxy clustering that trace out the underlying dark matter scaffolding. By studying how galaxies are distributed in space and how they cluster together, astronomers can test predictions of cosmological models and refine their understanding of how structure grows in the universe. One of the most powerful techniques Webb employs is gravitational lensing, where the gravity of a massive foreground object like a galaxy cluster bends and magnifies the light from more distant background galaxies. This natural magnification allows Webb to observe galaxies that would otherwise be too faint to detect, pushing observations to even earlier epochs and to intrinsically less massive galaxies than would otherwise be possible. Gravitational lensing has revealed some of the faintest and most distant galaxies ever observed, providing a glimpse of galaxy formation in its earliest stages. These lensed galaxies often appear stretched and distorted into arcs or multiple images due to the bending of light, and astronomers use sophisticated models to reconstruct what the galaxy would actually look like if the lensing weren't present. This technique has revealed galaxies with stellar masses as low as a few million times the mass of the Sun existing when the universe was only a few 100 million years old. These dwarf galaxies are thought to be the building blocks from which larger galaxies later assembled, and studying them provides insights into the initial conditions and processes of galaxy formation. The data Webb continues to gather is refining our picture of the early universe week by week and month by month. Each new observation adds detail to our understanding, sometimes confirming theoretical predictions, and sometimes challenging them. The process of science involves this constant dialogue between observation and theory, with unexpected discoveries prompting new ideas and new models making predictions that can be tested with further observations. Webb has clearly shown that the early universe was more complex and interesting than we anticipated, and this realization is driving a period of intense creativity and reassessment in cosmology. Some researchers are exploring whether modifications to the standard cosmological model might help explain Webb's findings. This doesn't necessarily mean abandoning the Big Bang framework or dark matter, but perhaps adjusting some of the assumptions about the early universe. For instance, the properties of dark matter, the nature of the first star forming gas clouds, and the efficiency of various physical processes might all need to be reconsidered in light of new evidence. Other researchers are working to improve the resolution and realism of cosmological simulations, incorporating more detailed physics to see whether models can reproduce the early massive galaxies that Webb has discovered. Still others are focusing on improving observational techniques to ensure that the measurements themselves are as accurate as possible. Determining the distance to a galaxy, its stellar mass, and its star formation rate all involve complex analysis of the light received, and each step in this analysis involves assumptions and potential sources of error. By carefully examining these steps and refining the methods used, astronomers work to minimize uncertainties and ensure that the surprises Webb has revealed are real and not artifacts of measurement errors or incorrect assumptions. What makes Webb particularly valuable is its combination of sensitivity, resolution, and wavelength coverage. Its large mirror gathers more light than previous infrared telescopes, allowing it to see fainter objects. Its location at the second Lagrange point, far from Earth's heat, allows its instruments to operate at the extremely cold temperatures needed for sensitive infrared detection. And its suite of instruments covers a broad range of infrared wavelengths, from the near-infrared, where the light from early galaxies is redshifted into, to the mid-infrared, where dust emission and the light from cool stars dominate. This combination allows Webb to study early galaxies in multiple ways simultaneously, building up a comprehensive picture of their properties. As Webb continues its mission, it's observing not just individual galaxies, but also large fields of the sky to build up statistical samples. Understanding whether the massive early galaxies Webb has found are rare exceptions or common features of the early universe requires observing many galaxies and determining what fraction have unexpected properties. Early indications suggest that while the most massive early galaxies are still relatively rare, there are more of them than expected, and moderately massive galaxies are quite common at early times. This distribution provides important constraints on theories of galaxy formation. Webb is also observing the same regions of sky repeatedly to search for changes over time and to build up deeper images by combining multiple observations. These deep fields reveal ever fainter galaxies and push observations to earlier and earlier epochs. Each incremental improvement in depth and sensitivity brings galaxies from slightly earlier times into view, allowing astronomers to trace the evolution of the galaxy population across cosmic history. By comparing the properties of galaxies at different redshifts, astronomers can see directly how galaxies change as the universe ages, watching cosmic evolution unfold. One of the most exciting aspects of Webb's discoveries is how they've opened up new questions that weren't even being asked before. Before Webb, the main question about early galaxies was whether we could detect them at all. Now the questions have shifted to understanding how these galaxies could be so massive, so structured, and so chemically enriched so early in cosmic history. These are harder questions in some ways, requiring deeper theoretical understanding and more sophisticated models, but they're also more interesting because they're pushing the boundaries of what we know. The discoveries have also highlighted how much we still have to learn about fundamental physical processes. Star formation, the mechanism by which clouds of gas collapse to form stars, is a process that operates on relatively small scales but has profound consequences for galaxies and the universe as a whole. Despite decades of study, many aspects of star formation remain poorly understood, especially in environments very different from the nearby universe. How do stars form in gas that has very few heavy elements? How do the first massive stars differ from stars forming today? How efficiently can stars form when gas is heated by intense radiation fields? These questions are crucial for understanding early galaxy formation. Similarly, black hole growth and the relationship between black holes and galaxies is an area where fundamental understanding is still developing. Why do black hole masses correlate so tightly with galaxy properties? How do supermassive black holes regulate star formation in their host galaxies? What were the seeds from which supermassive black holes grew? Webb's observations of early black holes are providing new data to address these questions, but they're also revealing that the answers might be more complicated than we thought. The chemical evolution of galaxies is another area where Webb is making important contributions. The abundances of different chemical elements tell the story of stellar nucleosynthesis and how elements are created and dispersed. By measuring element abundances in early galaxies, astronomers can determine what types of stars dominated early star formation, how rapidly supernovae enriched the interstellar medium, and how effectively gas was retained in galaxies versus being blown out into intergalactic space. These measurements are technically challenging because they require detailed spectroscopy of extremely faint objects, but Webb's sensitivity makes such observations possible. An important aspect of understanding early galaxy formation involves connecting observations across different wavelengths. While Webb observes in the infrared, other telescopes observe the same regions of sky in visible light, ultraviolet, radio waves, and X-rays. Each wavelength reveals different physical processes and components of galaxies. X-ray observations detect hot gas and active black holes. Radio observations trace cold gas and star formation. Ultraviolet light reveals hot young stars. By combining data from multiple telescopes, astronomers build up a comprehensive picture of what early galaxies were like, understanding not just their stellar content, but their gas properties, black hole activity, and overall energy budgets. Webb is also studying the role of the environment in shaping early galaxies. Galaxies that form in denser regions where many other galaxies are nearby might evolve differently than isolated galaxies. Interactions and mergers between neighboring galaxies can trigger bursts of star formation, disrupt galactic structures, and drive gas into central black holes. By observing galaxies in different environments and at different densities, astronomers can determine how much of galaxy evolution is driven by internal processes versus external influences from neighboring galaxies and the surrounding cosmic web. The question of reionization, mentioned earlier, remains closely connected to early galaxy formation. The ultraviolet light from stars in early galaxies was responsible for ionizing the hydrogen gas that filled the universe, transforming it from neutral to ionized, and making the universe transparent to ultraviolet and visible light. Understanding exactly when and how this happened requires knowing how many galaxies existed at different times, how actively they were forming stars, and what fraction of the ultraviolet light they produced could escape into the surrounding intergalactic medium. Webb's observations are providing crucial data on all of these questions. Some early galaxies appear to be quite efficient at allowing ultraviolet light to escape, with significant fractions of their UV photons making it out into intergalactic space where they can contribute to reionization. Others appear to be more opaque, with most UV light absorbed by dust or gas within the galaxy itself. Understanding what determines this escape fraction and how it varies between galaxies is important for modeling the reionization process. Webb has found that some of the earliest galaxies have properties suggesting they were major contributors to reionization, while others, despite being bright and massive, might have played a lesser role. The discovery of dust in early galaxies has been another area of interest. Dust grains are tiny particles formed from heavy elements, and they play important roles in galaxy evolution. Dust absorbs ultraviolet and visible light from stars and re-emits it as infrared radiation, affecting the energy balance of galaxies. Dust also provides surfaces where molecules can form, including the hydrogen molecules that are necessary for efficient star formation in cold gas. The presence of dust in galaxies only a few 100 million years old indicates that heavy elements had already been incorporated into solid particles, requiring multiple generations of stars to have formed, evolved, and died. Webb's mid-infrared instruments are particularly well suited to detecting and studying dust in distant galaxies. The infrared light from dust emission is redshifted into the mid-infrared at the redshifts of early galaxies, making it observable with Webb's capabilities. By measuring the amount and temperature of dust, astronomers can estimate how much star formation is hidden by dust and gain a more complete picture of the total stellar mass being formed. This is important because dust can cause astronomers to underestimate star formation rates if they only observe in ultraviolet or visible wavelengths where dust blocks the light. As Webb's observations continue and the data accumulates, our picture of the early universe is becoming simultaneously clearer and more complex. Clearer in the sense that we're actually seeing early galaxies in unprecedented detail rather than inferring their properties from theoretical models. More complex in the sense that what we're seeing doesn't fit neatly into the simple scenarios that previous models predicted. This combination of clarity and complexity is exactly what makes frontier science exciting. We're not just confirming what we already thought we knew, but discovering that reality is richer and more surprising than we imagined. The implications of Webb's findings extend beyond galaxy formation to cosmology more broadly. The early formation of massive galaxies and black holes puts constraints on the overall evolution of cosmic structure and the distribution of matter in the universe. If galaxies assembled more quickly than expected, this might indicate that the universe was denser or more clumpy on small scales in its early phases than standard models predict. Or it might mean that the processes that turn gas into stars operated more efficiently under early universe conditions. Either way, these findings will influence how cosmologists think about the broad sweep of cosmic evolution from the Big Bang to the present day. There's also a philosophical dimension to these discoveries. Humans have always wondered about our origins and our place in the cosmos, and understanding galaxy formation is part of that larger story. Galaxies are the cities of stars where planets form, and where the chemical elements necessary for life are created and dispersed. By studying how and when galaxies formed, we're learning about the conditions that eventually led to our own existence. The fact that galaxies formed earlier and developed faster than we expected means that the universe became a potentially hospitable place for complexity and life sooner than we thought. Looking ahead, Webb has many more years of observations planned, and each year will bring new discoveries and refined understanding. The telescope is observing not just the most distant galaxies, but also objects at intermediate distances that help bridge the gap between the early universe and the present day. By tracing galaxy evolution across cosmic time, from the first galaxies to modern ones, astronomers will build a complete picture of how galaxies grow, change, and interact over billions of years. Other upcoming telescopes and instruments will complement Webb's capabilities. Ground-based telescopes with enormous mirrors will provide even higher resolution observations, though limited to wavelengths where Earth's atmosphere is transparent. Future space missions might push even further into the infrared or provide different types of observations that reveal other aspects of early galaxies. The combination of data from multiple sources will provide an increasingly comprehensive understanding of cosmic history. Webb has shown us that the universe in its youth was already a place of remarkable complexity and dynamism. Rather than a simple dark age followed by gradual enlightenment, the first billion years of cosmic history were filled with dramatic events, rapid transformations, and the emergence of structures and systems more sophisticated than we anticipated. And this revelation should inspire both humility about how much we still have to learn and excitement about the discoveries still to come. Every answer Webb provides seems to raise new questions, each deeper and more interesting than the last. The massive early galaxies that initially seem to contradict our understanding may ultimately lead to a richer and more accurate picture of how the universe evolved. Science progresses not by confirming what we already believe, but by confronting unexpected observations and working to understand them. Webb has given us an abundance of such confrontations, and the astronomical community is rising to the challenge with new observations, refined theories, and creative thinking about what the early universe might have been like. In studying these distant galaxies, we're looking back in time to see the universe as it was billions of years ago, watching cosmic history unfold in the light that has traveled across space to reach us. Each photon detected by Webb's instruments carries information about events and processes that occurred when the universe was young, encoding in its wavelength and intensity details about the stars, gas, and black holes that emitted or affected it. By carefully analyzing this ancient light, astronomers are reading the story of cosmic evolution written in the language of physics and revealed through the stunning capabilities of this remarkable telescope. The story Webb is telling us is one of a universe more vigorous and inventive in its youth than we imagined, finding ways to build galaxies and structure with surprising speed and efficiency, setting the stage for everything that would follow.